My name is Qi Yufan, and my metric number is 226954. For my part, I want to introduce the Turing machine, how it works. And I will introduce from 4 parts. The part 1 is detailed explanation of the working mechanism of Turing machines. The part 2 is about the practical example of Turing machine operation. The part 3 is about the core principle of Turing machine. The mathematical definition of Turing machine is for part 4. The part 1, detailed explanation of the working mechanism of Turing machines. Initial configuration. The Turing machine starts operating from its initial state with a set of initial inputs on the paper tape. The read-write head is posted at a certain grid on the paper tape, usually starting from the first input symbol. The role of control rules. Turing machines use a transfer function to guide operations. Delete QS equal QSD. The Q is for current states. S is the currently read symbol. The Q is new state, and the S is to write symbols on paper tape. D is movement direction, left L or right R. Basic steps. The Turing machine operates in the following circle. Read the symbol of the current cell. Transfer rule. Determine the next operation based on the current state and symbol. Modify the symbol of the current grid. Move the read-write hand left or right. Switch to a new state. Repeat. Continue running until reaching the termination state or falling into an infinite loop. And for part 2, it's about a practical example of Turing machine operation. Problem is reserve the sign of binary numbers. Objective is convert 101 on the paper tape to 010. The first step, initial configuration. Input paper tape content 101. Represents space. Initial state Q0. Read or write head position, pointing to the first one. The second step is transfer function. Delete Q01 equal Q00R. Change 1 to 0 and then move to the right. Delete Q00 equal Q01R. Change 0 to the and then move to the right. Delete Q0 equal QFN. When a space is read, enter the termination state QF. The third step is action process. Step 1. Read 1 and write 0 and move the head to the right. Start 001. Step 2. Read 0, write 1 and move the head to the right. Start 011. Step 3. Read 1, write 0 and move the head to the right. Start 010. Step 4. Read a space and enter the termination state. The fourth step, final output, paper tape content 010. The Turing machine has stopped. Part 3 is about the core principle of Turing machine. About the limited state transition, the behavior of a Turing machine is driven by a finite state machine with control rules at its core. Each state transition determines the next operation. For the unlimited paper tape is both an input memory and an output medium of computation. simulating the memory and storage function of modern computers. Paper type can extend infinitely to the left or right, theoretically without a storage limitation. And for universality, Turing machines can simulate any computational process that can be described by through different state and transition rules. It is the theoretical foundation of general-purpose computers. For part 4 is about the mathematical definition of Turing machine. A Turing machine is a 7-2. M equal Q sigma gamma delete Q0 QF and B. Q is state set. Sigma is input symbol set. Gamma is a set of paper type symbol, just like sigma Q set gamma. Delete is transfer function. Q0 is initial state. QF is accepted state. Terminated state. B is black symbol. This is all my parts. Thank you for your listening.
Now we move on to example of Turing machine. So given that string W equal to 001, okay. So the input from this question, the first input is 0. So from the starting state, we accept input 0. So we follow this path, 0 will become an empty. So since it become empty, 0 here will disappear, and new state is Q1, and the state will move to the right side. So now it has been moved to the right side. Our new input is 0. So we input 0, 0 will become 0, and the state will be moved to the right side. So it has been moved to the middle of 0 and 1. So the state is here. And our new input is 1. We accept 1. 1 will become 1, and the state remain unchanged. Now the state is moved to the right side. So 0 and 1 is all the way on the left, and whereas Q1 is on the right side. So since there's nothing here, we can say that this is an empty. So our input is empty or nothing. We follow this path, which makes Q1 turns Q1 to Q2. And Q2 has been moved to the left side, as you can see, left side. So now it is in the middle of 0 and 1, Q2. Now the new input is 1. The new input is 1. We scan 1. We follow this path where 1 will become nothing. It will disappear. So Q2 has turned to Q3, and it is moved to the left side, which is on the left side of 0. And 1 has already disappeared. Now our input is 1, sorry, 0. And Q3 remained Q3 because our input is 0, so we follow this arrow. So 0 will become 0, and Q3 will move to the left side, which is right here. So since it moved to the left side from 0, an empty space appeared here, which is our new input. So we read this input, we follow this path, where Q3 will go to Q0, or the starting state, you may say, and Q0 will move to the right side. So from here, move to the right side. Now it is closer to our new input here, which is 0. From starting state, now there's a loop here, as we can see, because it is now at its starting state. So we read 0, we follow this arrow, we follow this path, and 0 will become empty. Now we are Q1. Q1, what's on this side? There's nothing. So we follow this path where empty will become empty again. Q1 will turn to Q2 and move to the left side. So now there's nothing here. So we can conclude that this is a rejecting configuration. Now for this new string, which is W equals to 0011, so from the starting state, our first input is 0. So from here, 0, as we can see, we follow this path where 0 will turn to empty. Now, one of the 0 here will disappear. Our new state is Q1 and the new input is 0. So we read 0, 0 will turn to 0, and Q1 will move to the right side. So these two switch place. 0 is right here, Q1 is right here. Our new input is 1. 1, we scan 1, so 1 will still remain a 1, and Q1 will move to the right side. So which is right here. This is the new place of Q1. And this is our new input. So again, 1 remain 1, Q1 move to the right. So now Q1 is all the way on the right side, and 0, 1, 1 are all the way on the left side. So there's nothing here. There's nothing here, so which means it is empty. If it's empty, we follow this path where empty will still become empty, remain unchanged, and Q1 will turn to Q2, but Q2 will move to the left side. So 1 and Q2 will switch places. Now it is 0, 1, Q2, 1. Now our new input is 1. We read 1, so we follow this path. 1 will turn to empty, and Q3 will move to the left side. So the 1 has already disappeared, and the 1 here has moved to the other side. Now our new input is 1. We read 1 from here, from Q3. 1 remain 1, but Q3 will move to left side. So now it is all the way on the left, and our new input is 0. From here we read 0. 0 will remain 0, and Q3 will move to the left side, which an underscore or empty, underscore indicates empty, will appear, and that's our new input. From this input, we follow this path where from Q3 it returns to our starting state. And now Q0 moved to the right, and our new input is 0. So 0 become empty, and Q1 moved to the right. So the 0 here already disappeared, and our new input is 1. So from 1, 1 remain 1, Q1 remain the same, but move to switch place with 1. And from here we see there's no number, so it's empty. From empty, we follow this path where Q1 will turn to Q2, and it switch place with Q1 again because Q2 will switch place with 1 again because it says Q2 must move to the left side here. And from here, our input is 1. From 1, we follow this path, and 1 will turn to empty, which means 1 will disappear. So Q2 has already turned to Q3, which leaves an empty here, and that's our new input. From Q3, if the input is empty, we follow this path where we are back to our starting point. And now from the starting point, is there an empty here? Yes. So from here, we can read this path. So we follow this path, and it will end at an accepting state. So from here, we can conclude that this is and accepting configuration. So that's all from me. We can move on to the application in real life.
Hello everyone, my name is Xia Jiangnan and my metric number is 227067, and today I'm going to introduce the theoretical foundations of computation about Turing machine. And here's my contents. Have 8 parts, and the first part, introduction of the Turing machine. The first part is what is a Turing machine? Here is a brief description. A Turing machine is an abstracter computational model introduced by Alan Turing in 1936 to define algorithms and computability. And the next one is key components of Turing machine. First one is tape, an infinitely long storage medium divided into cells. And the next one is read and write head. Read samples on the tape, writes new samples, and moves left or right. And next one is state register, tracks the machine's current state. Next one is transition function, defines how the machine moves between states based on inputs. And the last one is halting state, indicates when the machine stops. And here's a characteristic of a Turing machine. Universality can simulate any algorithm deterministic. Given the same input always produce the same output. Infinite tape idealize the assumption of unlimited memory. Halting problem. Not all problems can be solved. And next one's real-world significance. Real-world significance Turing machines lay the foundation for modern computing, basis for designing algorithms and understanding computation limits, connection to real-world computers, infinity memory versus infinity tape, and about Alan Turing's contributions. Alan Turing's contributions, including the Turing test and his impact on computer science and artificial intelligence. And here is an example of a Turing machine. Transition include a table or diagram to illustrate a transition. Example Q1 0. When reading 0, write 1, move right and change to state Q2. And the importance of Turing machines in theoretical computer science. Summary of Turing machines. A fundamental model of computation introduced by Alan Turing defines the limits of what can be computed and impact on model computing. Foundations of algorithm. Turing machines provide a theoretical framework for designing algorithms. Computability theory. They help us understand which problems can be solved by computers and which cannot. Universal model. Any algorithm can be simulated by a Turing machine, making it a universal model of computation. Thought-provoking quote. The Turing machine is not just a theoretical model, it's the essence of computation. Okay, that's all for my presentation. Thank you, everyone.
Hello, my name is Ma Jiayi, and my metric number is 226904. Today, I will going to introduce the Turing machine about its application in real world. First, introduction. Although primarily theoretical, Turing machines have many real-world applications in modern computer, software design, and problem solving. Foundations of computing. Turing machines provided the theoretical basis for modern computers. All algorithms running on a computer can be modeled using Turing machines, which helps computer scientists understand the power and the limitations of computing. Algorithm design and analysis. The concepts of decidability, complexity, and computability derived from Turing machines are essential for designing efficient algorithms and understanding which problems are solvable and which are not. For application, artificial intelligence, AI systems rely on computational models influenced by Turing's theory, especially in areas such as machine learning, automated reasoning, and cognitive modeling. Compiler design. Turing machines are used to simulate the processing of programming languages, guide the development of compilers and interpreters, and convert high-level code into instructions that can be executed by machines. Cryptography and security. Turing machines help study the complexity of cryptographic algorithms and evaluate the feasibility of using computational models to crack cryptographic systems. Automated theorem proving. Mathematical logic and formal verification techniques rely on Turing machine concepts for verifying the correctness of mathematical proofs and software systems to ensure mission-critical reliability. Data compression and encoding. Theoretical models inspired by Turing machines have guided the design of compression algorithms, such as Huffman coding, to improve the efficiency of data storage and transmission. Operating systems and process scheduling. State transitions and resource allocation in operating systems can be modeled using Turing machines to optimize process scheduling and resource management. Application in real world. Robotics and control systems. The Turing machine concept influenced the design of finite state machines, which are widely used in embedded systems, industrial automation, and robot control algorithms. Quantum computing. Theoretical models of computation, including Turing machines, can be used as reference frames to evaluate the advantages of quantum computers over classical computers. Natural language processing. NLP applications use formal language and automation theory, an extension of Turing machines, to efficiently process and analyze human language. Software verification and testing. Formal methods utilize Turing machine principles to verify the correctness of software, detect vulnerabilities, and evaluate whether it meets expected performance. About conclusion, although computers in the real world are finite in terms of storage, and ideal Turing machines are infinite, the concept of Turing machines remains an important foundation for driving the development of theoretical and applied computer science. That is all about the application in real world for Turing machines. Thank you.